Alrighty, lads and ladies, welcome back. Today is another fun day in the wonderful world of Calculus 2 because today we're going to meet our second notion of convergence. Apologies for running a little bit behind. Things are on the hectic side because my wife and I are trying to buy a house like right now. Turns out that the housing market in Gainesville is batshit insane. Like, compared to when I moved here in 2010, not only are the prices crazy, but the market is so aggressive that people are fighting. We found a house that went on the market Friday, toured it Saturday, and there were already 5 offers in by Sunday when we decided to make an offer ourselves. So I've been trying to talk to lenders and do all that crazy stuff. But that doesn't matter to you. What matters to you is what's going on here. Presumably, what matters to you most is getting your exam 1 grades. Now, I am still working on your class's stuff, but my rule is 1 week. I will always do my best to get your exams back to you within 1 week. So I'm hoping that before the end of the day today, I will have all of your scores and feedback in Canvas. Excuse me. Hello.
Yes, Professor Foster here. This is Jose going across the DRC.
Take care. Bye.
You too.
Oof, DRC. Must be training up some new people. Okay, so exam scores in today, and today we are going to learn our second notion of convergence. So we've been talking a lot about improper integrals and how improper integrals can converge or diverge. Today we're going to begin talking about sequences. Sequences are a totally different family of objects, and they are another family of objects which have the ability to converge or diverge. So there's only one place to begin when introducing an entirely new class of objects, and that's with a definition. I'm going to give you two definitions of the word sequence, and then we'll start moving forwards, kind of being conscious of both of those. Our first task today is to understand what the word sequence means. So we're going to begin sequences, which is section 11.1. So kind of formally, a sequence is a function whose domain is perhaps the whole thing or a subset of the natural numbers. And the natural numbers, that's the set we usually write as a capital blackboard bold N, like this. And depending on where you are, if you're in France or some other parts of Central Europe, you consider 0 a natural number. Otherwise, it's just the counting numbers, 1, 2, 3, 4, and so on. So this is like our formal definition of a sequence. A sequence is any function whose domain is either all of or some subset of the natural numbers. Remember what a function is, right? A function is a rule for pairing objects from one set to objects in another set, where each object in the first set is paired with one and only one object in the second set. Since the set of natural numbers is ordered, right? You go up, you can list the natural numbers, and also is discrete. If you think about plotting these on a number line, they form little separate isolated dots. What we're really doing here, when we say we're defining a function from the natural numbers to somewhere else, say the real numbers, is generating a list. So less formally, a sequence is a list. And generally, the range of this function, the set of outputs here, will be numbers. We could form a sequence of other objects, but for us, it is an ordered list of numbers. So one of the challenges in studying functions of a real variable is that there is no first real number. There is no second real number. In general, if you have your favorite real number, there is no next real number because they form a continuum. But the natural numbers, while they are ordered, that is not a continuum, right? There is a first natural number, the number 0. There's a second natural number, the number 1, and so on. When we describe a function algebraically, the typical notation would be like f of 1 is something, f of 2 is something, f of 3 is something, and so on. And remember here that because our domain is a subset of the natural numbers, maybe starting at 1, maybe starting at 0, it wouldn't make sense to talk about f of 1/2 or f of pi. And so we use the variable n to suggest that the inputs here are whole numbers, right? Because usually when you see the symbol lowercase n, it's implied that you're talking about a whole number. When referring to sequences, which are functions, right, like this, we don't usually use the function notation, though. There's a notation that is a little bit more convenient when talking about the things that we do with sequences. So if I have the sequence f, and it is, a function like f of 1, f of 2, and so on, instead of writing f parentheses 1 to indicate f of 1, we write f and then just a little 1 down here in the subscript. So instead of f of 1, we write f1 or f sub 1. Instead of f of 2, we write f sub 2. Instead of f of 3, we write f sub 3. And in general, instead of f of n, we would write f sub n. So this is the notation. Another kind of unique element of the notation here is that we don't usually use the symbol f, right? We're used to using f, g, h for our functions. For sequences, we usually use letters like A, B, C instead of things like F, G, and H. So instead of writing F1 or F2 or just naming the function F, we name the function A. Instead of naming the function G, we name the function B, and that sort of thing. Right? So the corresponding sort of notation here would be like, I'll just show. So the standard notation for sequences is like A1, A2, A3, A4, and so on. And I'll write down at the bottom here AN. Right, so still a function. Each one of these things, A1, A2, A3, are numbers. The inputs are the numbers 1, 2, 3, and so on. And these outputs, A1, we call these the terms. We would call this the first term. I would call this the second term. I would call this the third term. Fourth term. And in general, AN is called the nth term. So these things are functions, but they have their own special notation, their own special language, kind of special vocabulary. If I want to refer to the whole list instead of one of the terms, right? Like A3 is just one term, or AN is the nth term. But if I want to refer to the whole sequence at once, last bit of notation, I promise we'll look at examples. When referring to the whole sequence at once, we write curly braces, AN. And then often you'll have something down here like n equals 1 to infinity up here. And this is the sequence whose terms are A1, A2, A3, A4, A5. And it's just that. It's an infinite list of objects, usually numbers. The number that you see down here on the bottom right, the n equals 1, tells you where the sequence starts. Remember we said that the domain could be the whole natural numbers or some subset of the natural numbers. If I'm talking about the sequence Bn, and his domain is 0 to infinity, just the natural numbers, then I would write like this to refer to the whole sequence. That's all. Okay. So these are the names of the things and the notation that we use when referring to them. We're going to do lots and lots and lots of different stuff with sequences. And I think the first thing to do is just list out some terms. So let's give ourselves a sequence and list out some terms. See if we can get comfy doing that. So let's say list the first 5 terms of the sequence an going from n equals 1 to infinity, where the formula for the nth term is n plus 1 over n. So here, referring to the whole sequence, its name is an, or just a, and the nth term, an, can be calculated through this formula. Listing terms is not challenging. It's like we were writing over there. I'm just going to say, okay, A1, A2, A3, A4, and A5. Those are the things I'm looking for. And we're given a formula for the nth term. So if I want the first term, A1, I'm just going to plug in 1 for n here. And I get 1 plus 1 over 1, which is 2. I'll write it out. 1 plus 1. And that's 2 over 1, or just 2. A2, I would plug in n equals 2. That's going to give me 2 over 2, which is 3/2. A3, 3 plus 1 over 3, which is 4/3. A4, 4 plus 1 over 4, which is 5/4. And A5 is 5 plus 1 over 4, which is 6/5. No, nothing crazy. If I give you a formula for the nth term and ask you for the first few terms, that's very straightforward. You're just plugging in some numbers. It's quite common to go the other way as well, where I give you the first few terms and I ask you to find for me a formula for the nth term. So I give you the purple and you give me the black instead. Let's try something like that. So let me say that an, the sequence an, and sometimes when you don't want to specify or you're okay with somebody changing it on you, you don't need to write the value of n down here, right? So I'm writing the curly braces an, but I'm not specifying that n starts at 1 or n starts at 0, and that's okay. I'm going to list the first few terms here as 0, 2, 4, 6, 8, 10, and so on. And this notation you will see in your homework and in the book as well. Sometimes rather than having a formula or the symbols AN in here, they'll write curly braces, meaning we're talking about the whole sequence as a singular object, and then just list some terms. When you see these dot, dot, dots, these are called ellipses. Those mean that the list goes on in this same fashion, right? So the pattern continues like this forever and ever. Let's see if we can do this for the sequence Bn, whose first few terms are 1, 3, 5, 7, 9, 11, and so on. And we'll do one more here. The sequence Cn, whose first few terms are 2, 4, 8, 16, 32, 64, and so on. We're just trying to go back the other way. They're giving us the first few terms of the sequence and asking for a formula instead of giving us the formula and asking for the first few terms. You may see things of this nature showing up on like Facebook or wherever. It's like, find the pattern, tell me the next thing. It's that sort of thing. Looking at the first sequence here, AN, how would you describe this in words? If I just give you this list of numbers and I asked you to tell me what these numbers are, or describe these to me, how would you describe them? Not a trick, don't overthink it. Yeah, so I got a DM there that says even numbers, right? This is the list of all the even numbers. 0, 2, 4, 6, 8, and so on. What makes an even number even? Now, there's multiple right answers here. I promise I'm not trying to trick you. Yeah, another DM there says divisible by 2. So if I say that n is divisible by k, algebraically what that means is n is equal to k times some other integer, right? So if I tell you that a number is divisible by 2, i.e. that number is even, that means that number is equal to 2 times some other number. So let's try, having thought of this, writing each of these as 2 times something. This will help us get what we want. This first guy is 2 times 0, and 2 times 1. 4 is 2 times 2. 6 is 2 times 3. 8 is 2 times 4. 10 is 2 times 5. And if I asked you for the nth number in this list, well, let's see, we've got 2 times 0, 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. That would be 2 times n. So here we would say that an is 2 times n. And I could describe the sequence like this. i.e. an is just 2n. Is everybody comfortable with how we arrive at this formula for the nth term? Any questions about the notation? Okay, let's try the next one. Same sort of thinking. If you had to describe the numbers in this list, how would you describe them? This is the list of yeah, these are the odd numbers, right? And again, the key is going to be to characterize those numbers. So what makes an odd number odd? Even numbers are all the numbers that are divisible by 2. What are the odd numbers? Or do you see a relationship between the numbers in the first list and the numbers in the second list? Yeah, yes, exactly. An odd number is a number that is off from an even number by 1. So if you add 1 to 0, right, you get 1. If you add 1 to 2, you get 3. If you add 1 to 4, you get 5. If you add 1 to 6, you get 7. Every number in this list is a number from this list plus 1. So in other words, I could say that this sequence is the sequence 2n plus 1, where n runs from 0 to infinity. Or you could just say that bn is 2n plus 1. Yeah. Okay, what about this last guy? Very good. These are powers of 2, right? This is 2 to the 1. This is 2 to the 2. This is 2 to the 3. This is 2 to the 4. 32 is 2 to the 5. 64 is 2 to the 6. So in the curly braces notation, I would say that this is 2 to the n. Now, the difference here is that the starting value for n is 1, right? These guys both had n starting at 0. To get the first number in the list for bn, you plug in 0 for n here. To get the first number in the list for an, you plug in 0 for n. To get the first number in this list, if we're using this formula, 2 to the n, we would plug in 1 for n. So I would write him this way in the curly braces notation. And if I was just trying to give you the nth term, I would say Cn is 2 to the n. That's it. So these are our answers. The problem asked for a formula for the nth term. Here's the formula for the nth term of each of these sequences. Not too hard, kind of fun, actually. And as these get more complicated, they require a little bit more creativity, but it's always this kind of fun, find the pattern. I want to make a little note before we move on from this. I know I don't want to bore you, but there is one little subtlety here. The choice to start the sequence at 0 or 1 really is a choice. Each sequence above could be written with n starting at n equals 0 or n equals 1. So I think the first two especially are much more natural to start writing with the first term having n equals 0. But if you wanted to, for whatever reason, have these sequences start at 1, for example, if you're given this problem and told to assume n starts at 1, which some of your homework problems will do, you would need to take this kind of very natural way of writing the thing and find a way to write it where the numbers match up, but this one comes from plugging in n equals 1, and this one comes from plugging in n equals 2, and so on. So for part A, we could write an equals 2 times n minus 1 instead of 2 times n. Because then when you plug in 1 for n, you get 2 times 0. When you plug in 2 for n, you get 2 times 1, and so on. So if I insisted that n starts at 1, I would write that as 2 times parentheses n minus 1. For part B, if I wanted to start this guy at n equals 1 instead of at n equals 0 and still have him generate this same list of numbers, same trick, just swap n for n minus 1. And when you do that, you distribute this 2, you get 2n minus 2 plus 1, that's 2n minus 1. And in part C, here he was most simple to write down with n starting at 1, but if I really wanted to, I could make that sequence start at n equals 0 by changing the n to an n plus 1. Now when I plug in 0 for n, I get 2 to the 0 plus 1, which is 2. When I plug in 1 for n, I get 2 to the 1 plus 1, which is 2 squared, or 4. So you can describe any sequence as starting at 0 or starting at 1. It's totally up to you unless the problem specifies. And if you need to change from one to the other, that's not hard. You just have to think about a little bit. If the most natural way to start the sequence is at 0 and you want to start it at 1, swap the n for n minus 1. If the most natural way to write down the sequence has it starting at n equals 1, but you want to make it start at 0, swap the n for n plus 1. It's like shifting up or down 1 in the list. Any questions on the purple or the blue? Moving on then. I can give you a formula for the nth term and ask you to list the terms. I can give you a list of the first few terms and ask you for a formula for the nth term. But none of that really feels even vaguely like calculus. The key thing we needed to get started with calculus operations back in Calc 1 was a good knowledge of graphs, right? You spent a lot of time looking at and learning how to make and inferring about functions from their graphs. Just like we can graph a function, we can graph the function f of x by plotting all the points in the xy plane of the form x comma f of x. In that same way, we can graph a sequence a sub n by plotting all points of the form n comma a sub n. Right, the graph of a function is ordered pairs where the x-coordinate is the input and the y-coordinate is the output associated with that input. right? Like if you want to find f of 3 on the graph of a function, you go to 3 on your horizontal axis, go up to the y value on the graph there. That y value is f of 3. In the same way, we can plot input-output pairs for sequences. Let's look at a quick example. I can sketch the graph of the sequence AN, where the nth term is given by the formula -1 to the n over n. Plane. The word after xy here is plane. So in the xy plane, sorry about that. So when we graph function of a real variable, we expect a curve or a line, some connected set in the plane. Maybe it's got a jump or a vertical asymptote, but generally curves are what we expect to see. When we graph a sequence, because the domain is a discrete set, it is not a connected set, it is not a continuum, we're not going to get a curve. But we can do this the same way you started learning how to draw graphs in 7th grade and make a little table. I left this off, I should say, and where n1 is from 1 to infinity. Clearly, we cannot start the sequence at 0. If we plug 0 in for n, it would be undefined. So we're going to plug in n equals 1. If I plug in 1 for n here, I get -1 to the 1 divided by 1, which is -1. Just listing the first few terms, but I'm listing them in a queue. If I plug in n equals 2 here, I get -1 to the 2, which is 1, divided by 2. This is positive 1/2. If I plug in n equals 3 here, I get -1 cubed divided by 3. -1 cubed is -1, so this is going to be -1/3. If I plug in 4 for n, I get -1 to the 4 over 4, and -1 to the 4 is positive 1, so this is 1/4. 2 more, 5 and 6. If I plug in 5 for n here, I get -1 to the 5 divided by 5. Because 5 is an odd number, -1 to the 5 is -1, so this is -1 over 5. And when I plug in 6 for n, I get positive 1/6. Then you notice a pattern here, right? Negative, positive, negative, positive, negative, positive. And each time the denominator just goes up by 1. So you could write as many of these as you want. You could do it quite quickly. But we're not just trying to list terms. We want to draw a graph. Your horizontal axis, when you're graphing a sequence, is not the x-axis, but the n-axis. And your vertical axis, you can still call that y. Instead of writing y equals f of x, we would say y equals an. And we usually just read it, you've probably noticed, as an. You can say a sub n if you want. You can say a of n if you want, but please don't say a to the n, right? This is not a power, and that can be quite confusing. So when you refer to the sequence, you can call it an, a sub n, a of n, but not a to the n. I'm going to draw a graph here, so I need to think about an appropriate scale for both of those axes. My horizontal scale, well, are just going 1, 2, 3, 4, 5, 6. So it's nothing too fancy there. 1, 2, 3, 4, 5, something like that. My vertical scale, ooh, and I've actually set myself up quite poorly here. That's okay. My vertical scale, I've got values running from -1, +1/2, -1/3. So let me mark this down here as -1. And I'll mark this up here as +1. The first ordered pair on this graph is going to be 1, -1, which is this point right down here. The next ordered pair on my graph comes from the second row of the table. It's 2, +1/2. So that's 1/2 is right about there. Something about like that. Well, the next ordered pair would be 3, -1/3. So third of the way down to -1. Something like this. Then we have 4, +1/4 here. 5, -1/5 should be about here. And 6, +1/6, which would be about here. So this is a reasonable graph of this sequence. What we don't have here that we're used to having when we look at graphs is a curve connecting these points, right? Usually when you draw a graph of a function, you plot a few points and then find a smooth curve that connects those points. But with a sequence, because the domain is just the whole numbers, there is no point on the graph at x equals or n equals 3.5. 3.5 is not in the domain because we're talking about a sequence, and the domain of a sequence is just the natural numbers. What that means is the graph of a sequence is a set of isolated dots. No curves. We don't connect the dots, we just have the dots. Is it possible to find curves that connect these dots? Yeah, it is. And we will actually have a theorem. We're not going to get to it today, but we'll have a theorem that talks about those curves that connect the dots from the graph of the sequence. But the graph of the sequence itself is just the dots. And now these dots do continue, right? The next one we would expect to be like here, if we're following this pattern. The one after that we would expect to be up here. And you notice a pattern, right? Right? But it continues on like this forever and ever and ever on end. Questions about coming up with the graph of a sequence? Okay. I want to talk about some consequences of this blue observation here. If the graph of a sequence is just a set of isolated dots, why do we talk about it in calculus? In other words, what sort of calculus operations can you do with something like that? Clearly, this is a calculus class. I intend to do some calculus at some point with these things. Calculus operations can we do with sequences? You may remember from Calc 1 that in order to differentiate a function, that function must at least be continuous, that differentiability is a stricter criterion than continuity. So let's ask some fun questions. Can we talk about continuity? Can we talk about differentiation? Can we talk about integration? Can we talk about limits? These are the main operations that we encounter in calculus, right? Specifically, differentiation and integration. Let's begin at the top though. Continuity. Is this the graph of a continuous function? It is the graph of a function. Is it continuous? I'm not going to bite your head off. What are your thoughts? If somebody just handed you this graph, they're a pre-calc student or something like that, and asked, is this continuous? What would you say? Yeah, no, it's not, right? Continuous, remember, means connected, right? One solid piece. And the formal definition of continuous requires taking limits, right? F is continuous at A if the limit as x approaches A is equal to f of A. I can't talk about the limit as n approaches 2, right? Because that means I'd have to talk about like a right limit and a left limit being equal. But there is no part of the graph here, and there is no part of the graph here. So I can't talk about approaching 2 from the right or approaching 2 from the left. The whole concept of a limit as x goes to 2, or any finite value here, is out the window. So this is a big no. Continuous basically means connected. And these are just dots. Right? So there's no way for them to be connected. They're all isolated dots. So if these things can't be continuous, is it possible that they are differentiable? Could I take a derivative? Can I talk about a tangent line to this graph at x equals 6? Yeah. Certainly not, right? Again, what would it be tangent to? Right? To be tangent, you need like a curve, and then you can be tangent to that curve, perhaps. But you can't be tangent to a dot. Derivatives are built out of these limits at finite values. So no, differentiable, let's write it as diffable, is kind of equivalent to the idea of being smooth. And again, these are dots. You're not continuous, then you're definitely not smooth. Yeah, smooth. Smooth. Right. If you're not even connected, there's no way for you to be smooth. So derivative differentiation is out. I'm not going to do that. I'm going to skip over integration for a minute because it turns out that's a fun question to, even in this very, very general way, try to answer. There is no limit in this one. I can't convince myself on that. Maybe it's one of those. But limits. Let's skip over integration and address limits for a minute. I've already said I cannot take the limit as x goes to 2 or the limit as x goes to 3 because there is no piece of the graph between 2 or 3. So I can't talk about the limit as x approaches 3 from the left or the limit as x approaches 3 from the right. But there is a sense in which I can talk about a limit here. So saying something like lim n to 2 of an can't make sense. Because left and right limits aren't possible for a sequence. Yeah, I'll just leave it at that, right? Because the sequence is just a collection of isolated dots. There's no way to talk about a left or right limit, which means there's no way to even define the idea of the limit as x goes to 2, or limit as n goes to 2 or n goes to 3. However, there is a very concrete way to talk about the limit as n goes to infinity of a. Description. So I can ask, what do these dots get closer and closer and closer to as we go further and further and further to the right? That is one very real way I can talk about a limit for a sequence. The limit as n goes to infinity. You remember from section 2.6 in Calc 1 that limits as x go to infinity are actually the formal way of defining this blue dotted line for a continuous function. This blue dotted line, that's the line y equals 0. If we were talking about a continuous function, what would you call that line? What's the name for a line that the function gets closer and closer and closer to? Feeling shy this morning. An asymptote, right? Asymptote. So we can talk about horizontal asymptotes for sequences in a meaningful way. We can talk about, therefore, limits at infinity for sequences in a meaningful way. And that's what we're going to do. Now, before we do that, I want to address this missing one, right? Integration, question mark. I can't talk about the area under a point, right? If I try to find the area under this curve, or under, it's not a curve, I try to find the area bounded by this graph and the horizontal axis, that area would be 0, because these points are the only thing on this graph, and every point, although we don't draw them that way, every point is actually infinitely narrow, right? A point is a 0-dimensional thing. So there's no way to talk about the area under this point or under that point. They would all be 0. And if you wanted to integrate and find all of that area, you're just going to get 0 every time. So I'm going to say kinda. There is no notion of area under a single point. But there is something we can do. Think Riemann sums. Think about good old Bernard Riemann. I could let this point define the height of a rectangle. I could let this point define the height of a rectangle. I could let this point define the height of a rectangle, and so on. Each one of them, because the horizontal distance between any 2 points here is 1, each rectangle would have an area. It would be a height times a width. The width of each rectangle would be 1. And therefore, the area of that rectangle would just be the height. So the area of the rectangle I'm displaying right now would be 1/2, because its width is 1 and its height is 1/2. If we're thinking about signed areas, this guy, I would measure his area as -1/3, right? Because he's got a negative height there and the width is 1. This guy would have area +1/4. This guy would have area -1/5. In other words, the areas are just these things, the outputs from the sequence. So if I want to talk about all the area of all those rectangles, that would be the same as adding up all the outputs or terms from the sequence. And that's going to be a big, big deal. The things we get out of this are called series. And series are kind of like type 1 improper integrals, right? If I wanted to add up all those rectangular areas, that would be similar to integrating this sequence from 1 to infinity. And indeed, we're going to use a lot of the theory from 7.8 when we talk about series. But before we do that, we need to get much more comfortable with limits. We need to practice working with limits a lot. So what I'm going to do for you now is define the limit of a sequence. There's only one limit we can take. It's the limit as n goes to infinity. Yeah, that's correct, Fabrice. The only calculus operation we can perform on sequences is limits, and only one kind of limit. I can't take the limit as n goes to 0 or as n goes to 5, but I can take the limit as n goes to infinity. There is a very real and concrete sense of that. Right? So like here, I would want to say that the limit as n goes to infinity of this sequence is 0, because the terms get closer and closer and closer to 0 as n gets bigger and bigger and bigger. If you list these numbers, they get closer and closer to 0, right? This is -1, 0.5, -0.333, +0.25, -0.2. I forget 1/6 of a decimal, but these numbers, if you list them or think about them as decimals, they get closer and closer and closer and closer to 0. Talk about limits of sequences. We say the limit as n goes to infinity of an, that is a sequence, is equal to the real number L provided I'm going to use some funky language here. Just think along with me, provided the terms of the sequence AN can be made arbitrarily close to L by taking N sufficiently large. Obviously, this is a very qualitative definition, right? There's not a lot of numbers in here or inequalities or things like that, but each of the underlying terms can be re-expressed mathematically. Intuitively, what we're talking about here is horizontal asymptotes. So let me just add that in here. Think when n to infinity an equals L, that's saying that y equals L is the horizontal asymptote. Okay, that's intuitive. Concretely, what we're saying here is that if you specify some window about L, so you've got a sequence, you look at its graph, the terms of the sequence appear to get closer and closer to the horizontal line y equals L as you go further, from your perspective, further and further to the right. What we mean there, if we want to be very, very quantitative, is that if you specify a window around the line y equals L, say L plus epsilon, L minus epsilon, here's your line y equals L, you specify a window, that I can guarantee all but finitely many terms of the sequence will live within that window. In particular, from some point on, all the terms will live in that window. So there's a picture. We'll look at concrete examples in just a moment. I'll say here is L. Put L in as a black dotted line. One, two, three, four, five, six. And here's the idea. If you specify a little window about L, so it's usually called an epsilon window, but we're not going to get too freaky with this stuff, so don't panic. You specify a little window about L. What this definition is saying is that the terms of the sequence will get as close as you want to L by taking n to be big enough. So maybe the terms of my sequence start down here. And they're creeping up and getting closer and closer and closer. But what we're going to say is that as long as all the terms of the sequence end up inside this window past some capital N, that the sequence is converging to L. so that the limit of that sequence is L. So I don't care what happens over here. These terms could jump down here, could jump way up here. They could have 5 of them sitting right on this line. But as long as there is some capital N for every epsilon window, no matter how tight it is, right? Maybe it's like this tight. As long as there is some point along the horizontal axis, where beyond that point, all the terms are within that window, we'll say that the limit is L. So again, just think horizontal asymptote and you'll be safe. If you're looking for a nice complete picture, usually the width of this window, we'd say is 2 epsilon. So this would be L plus epsilon, would be L minus epsilon. I'm not going to go into the delta epsilon thing. But this is the picture. Right? And the textbook has a version of this picture that is certainly better than the one I'm hand drawing. Share that with you. My share turned off, didn't Zoom? I see. Here we go. So here's the picture of a sequence having a limit, right? The terms of the sequence are getting closer and closer and closer to this line y equals L. And here is your epsilon window about L. And the idea is that from some point on, all the terms of that sequence will be within the epsilon window. It gets in there and it gets trapped. And we say that that sequence has limit L if no matter how tight that window is, you can find some capital N such that to the right of capital N, all the terms are trapped in that window. That's so the little symbol there, it's like a backwards 3 or a kind of curly lowercase e. And it's the Greek letter epsilon. So in ancient Greek or even modern Greek, this is the symbol that makes the eh sound. All right. Good news. All the shit you learned about limits from continuous functions carries over here. All that stuff that you learned about taking limits of regular functions can be applied to sequences without any hesitation. Specifically, there's this theorem that says if f of x is a function and f of n is the same as an, meaning when you plug whole numbers into this function, you get your sequence an, then the limit as n goes to infinity of an is the limit, same as the limit as x goes to infinity of f of x. So this theorem is why that good news is true. And all this is saying is that you can do all the shit with sequences that you did with functions. So renormalizing, dividing out top and bottom, the largest power of n, all of it. Even L'Hopital's rule will carry over. All right. Concrete examples. That's enough crazy theory. Let's do some concrete examples. That sequence we looked at? Oh, yeah, we can go back here. So when we started out, the first sequence we listed some terms of was that sequence an equals n plus 1 over n. That is a sequence where we can calculate the limit. And the limit work there is not nasty. Okay. It's never a bad idea to look at the graph. Here's my n-axis. Here's y equals a sub n. The numbers we got there were like a1 plus 2. A2 was 3/2 or 1.5. A3 was 4/3 or 1.333333. A4 was 1.2. Sorry, 1.25. A5 was 1.2. And a keen eye will suspect that those dots are starting to pile up on the line y equals 1. And A6, if we keep going, right, A6 would be like here, and here, and here, and here. So it looks like from the graph, it appears that the limit as n goes to infinity of an is equal to the number 1. Because the terms of the sequence get closer and closer and closer to 1 as n gets bigger and bigger and bigger. Or geometrically, the line y equals 1 appears to be a horizontal asymptote for the graph. But what we need is not a guess. This is a really good guess, but it's just a guess. To show this, we use normal limit stuff. So let's do it. The limit as n goes to infinity of an, well, an is n plus 1 over n, so that would be the limit as n goes to infinity of n plus 1 over n. And there's several ways to calculate this limit. You can renormalize, where you divide top and bottom by the largest power of your variable here. So I'd divide top and bottom by n. You could actually use L'Hopital's rule, right? Even though sequences, you can't talk about the derivative of a sequence. We had that theorem on the previous page that, well, if your sequence matches up with a continuous function, then you can calculate the limit of that continuous function. It'll do the same thing. That's what allows us to do all the normal stuff. So yeah, you could use L'Hopital's rule here if you wanted, because the top and bottom will both go to infinity. But I think by far the nicest thing to do here is just a teensy-weensy bit of algebra. N plus 1 over n. Remember when we talked about strategies for integration, can you just simplify that a little bit? Same sort of shit here. That's n over n plus 1 over n. And n over n is 1. This is the limit as n goes to infinity of 1 plus 1 over n. And one of the theorems we discussed back in section 7.8 was that like 1 over a positive power of your variable will always go to 0 as your variable goes to infinity. So this piece right here, 1 over n, he's going to 0, right? 1 over infinity is 0. So this limit is 1 plus 0, which is 1, as we suspected. And the graph is a great way to have a guess. It's a great way to get a feel. But when you go to show solutions to these sort of things, or as you go to work more complicated problems, you need to go through the work like this. So really the theorem that we had for continuous functions, 1 over x to the p will go to 0 as x goes to infinity, can be applied here. 1 over n to the p will go to 0 as n goes to infinity. Okay. Before I let you go, let me share with you just one last thing here, and we'll wrap up. Looking pen, please. We say the sequence AN converges to the number L if the limit as n goes to infinity of AN is equal to L. This is what it means for a sequence to converge. L must be a finite real number if the limit as n goes to infinity of AN does not exist, or is plus or minus infinity, then we say that the sequence AN diverges. So this is your second notion of convergence. We have a notion of convergence for improper integrals, and we have now a notion of convergence for sequences. They're very different things, but they have some similarities. These are infinite processes leading to finite results in the case of convergence, and divergence just means fails to converge. When we get to section 11.2, we're going to have a third notion of convergence for series, and all three of these will be different. And if you take an object like an improper integral, a sequence, or a series, you can build them out of the same algebraic stuff, like 1 over x, 1 over n, and sigma 1 over n. The answer, does this converge or diverge, will depend on whether you're talking about an integral, a sequence, or a series. So you need to keep these notions of convergence separate. I recommend having a page in your notes, potentially some flashcards, where you can look to see exactly what it means for an integral to converge, for a sequence to converge, and for a series to converge. And we need to be clear on the differences between those things, specifically between sequences and series. So put this somewhere in your notes. Consider having a dedicated page in your notes for like notions of convergence. Consider making up some flashcards, and be sure as we move on that you are understanding entirely what it means for each of these families of objects to converge or diverge. Next time it's going to be more sequences. We're going to be in 11.1 for a minute because it's actually a really big section. We will cover a handful of theorems and look at a lot more examples. For now, you do have a new homework set, and it's mostly list the terms of the sequence, or here's the first few terms of the sequence, try to find a formula for the nth term, or graph this sequence and guess at the limit. There are also a bunch of problems that have you just straight up calculating limits, and on those problems, you need to be doing this sort of thing, right? Not just guessing. We will talk a lot about those old rules from Calc 1, and I'll give you lots of practice and kind of remind you of the squeeze theorem and L'Hopital's rule and all that shit. You're gonna need it all. right? You're going to need it all. So you might want to take a little bit of time and look back at 2.6 or watch some YouTube videos, whatever works well for you. Of course, on my YouTube channel, if you want, you can look. I've got stuff from several years of Calc 2 and Calc 1 online, and you can watch some of my limits at infinity from Calc 1 stuff to kind of bone up on that if you like. Or if you want other materials, just let me know. I can find you stuff. But that's it. I've taken up enough of your time for today. I hope you guys have a lovely rest of your day. And if there's anything I can do to help you, please don't hesitate to reach out or come to office hours. Canvas message, Discord. Y'all know the drill at this point. Yeah, that's all. So I'll see you guys on Wednesday. Take care.